Hey everyone, ever wonder why some AI models ace their tasks while others stumble? It's not just about raw power or data size, it's about a delicate dance between two hidden forces, bias and variance. Let's break it down. Imagine training a model to spot cats in photos. If it's too simple, it might always guess cat, even when it's a dog, high bias like a compass stuck pointing north. But if it's overly sensitive to tiny details, it might memorize every photo it sees, failing to recognize new ones, high variance like a shaky hand that can't draw a straight line. The secret? Finding the sweet spot between these two. But how do researchers actually measure this balance? In this study, they used bias-variance plots. Think of them as a dashboard showing how different training strategies, called cooldown shapes, affect performance. Cooldown shapes are like recipes for how a model learns over time. Some start strong and fade, others ramp up gradually. Here's the twist, they track two key metrics. First, bias, how far the model's average guesses are from the truth. Second, variance, how much its answers change with different data. They tested these on two types of plots. One based on loss, how wrong the model is, and another on model weights, the internal numbers that define the model. The results? Strategies like SQRT or lowered linear cooldowns struck a better balance than others. But wait, there's a catch. When they measured variance through weights instead of loss, the results got skewed. It's like using a bent ruler to measure a mountain, useful but not entirely clear. They even tested smaller models and different datasets. And guess what? The same balance issues popped up again. This suggests these trade-offs aren't flukes. They're fundamental to how models learn. Oh, and here's a kicker. Turning off weight decay, a technique that keeps models from getting too complex, actually helped some strategies shine. It's like giving a runner a lighter backpack. Suddenly they can sprint faster. Now let's pivot to the optimizer world. Ever wonder why some AI models train faster or perform better than others? The answer lies in the optimization process, specifically the AdamW optimizer. This tool adjusts model parameters during training, but its effectiveness hinges on two critical parameters, beta 1 and beta 2. Think of beta 1 and beta 2 as the model's short-term memory. Beta 1 controls the momentum term, while beta 2 manages the adaptive learning rate. Together, they determine how the optimizer remembers past gradients. But here's the twist. The token half-life of these parameters, their influence over time, can be suboptimal. A recent study explored how tweaking beta 1 and beta 2 affects performance. They tested a scheduler called WSD, warm-up stable decay, which includes a cooldown stage, a period where the model settles in after rapid learning. Surprisingly, adjusting beta 1 and beta 2 to match a specific token half-life deteriorated performance for large batch sizes. But when they kept parameters unchanged and increased batch size, results improved significantly. This suggests that default AdamW settings might be better than we think, especially when paired with larger batches. It's like driving a car. You don't always need to tweak the engine if the fuel quality is high. The research also delved into beta 2's role. They found that larger beta 2 values consistently led to better performance. Why? Because a higher beta 2 extends the optimizer's memory of past gradients, helping it avoid overshooting the optimal solution. It's like giving the model a longer retina to track the path to success. To make this tangible, the team mapped the loss landscape, a 3D representation of how the model's error changes during training. They used a metaphor, the river valley. During cooldown, the model flows down this valley toward the best solution. Their plots showed this valley clearly at the start of cooldown, shrinking as the model approaches the optimal point. This gives us a powerful image of how optimization works in real time. So what's the takeaway? Small changes to hyperparameters like beta 1 and beta 2 can have massive effects, but sometimes the default settings are already optimized for modern practices like large batch training. And when it comes to bias-variance trade-offs, the right cooldown strategy can make all the difference. Whether you're a researcher or a curious learner, these insights highlight how nuanced AI training really is. The next time you see a model perform exceptionally, remember, it's not just about the model itself, but the invisible dance of parameters, schedules, and trade-offs behind the scenes. Thanks for watching. If you want to dive deeper into the math or explore the experiments, check the links in the description. Stay curious and keep pushing the boundaries of what AI can do.